few words only. Okay, good to hear. Very nice. Sometimes it's really complicated with amplifiers. You can make it even more. So you don't get scared. Sometimes it's then no, but it's nice to hear. Point now, really, how to start. I will use a couple of words to tell you where I come from. Of course, it's mentioned already, but it might be nice for you to see where I come from. And then actually, this is only 3 slides. Maybe just 10 minutes, and then I will start the real teaching of the real course. This is more like information. Now, what we have here. Okay, I don't have a pointer, but where I have it. There's it. Okay. Right? Yes, right. So the point really that I'm coming from Finland is here. It's really the Nordic countries, so this is Africa, of course, this is Russia, China, here, Australia. For some reason, I can't count the United States, but of course, this is not in real scale. So India looks very small, but actually it's not a small country, also China. Finland is quite big country, so I'm here in a really bigger sphere, I'm really close to the Arctic Circle and North Pole. And the point is, our capital is called Helsinki. I'm not from Helsinki, I'm a little bit further north from Helsinki. I will show you the next slide where I come from. But that's the idea. I have a direct flight to Delhi. And before we were able to use the Russian airspace, so more or less direct flight here for 6 hours. But now, based on the reasons, the Russian airspace is closed, so we have to go through here. And it's 8.5 hours. So the flight is 8 to 9 hours in there. And the distance is there. The point is, where are we? So if you look for geographically where Finland is, we are between 60 and 70. And the Arctic Circle is 66. So 1/3 of Finland is actually above the Arctic Circle. So we are an Arctic country. So we have really temperatures way below zero. We discussed yesterday before that the maximum difference between the maximum and the minimum temperature in Finland has to be 72 degrees. So in winter it was minus 37. And in summer it was plus 35. So we can have this 30-degree temperatures nowadays during the summertime, but that comes mainly from the global warming. So the global warming has a big impact here when you are close to the poles. In here, when you are, you see that the storms are more heavier and more strong. But that's the idea. So we have been 8 to 37 roughly. And then, if you look for the size of Finland, so it's 338,000 square kilometers. So it's quite big. I think we are the 5th biggest, so this is of course lying, for France is bigger than Finland. Sweden is slightly bigger than Norway now, so these are roughly the same scale, but Germany and France are big countries also, and India. But the point is the population. We discussed about the Kolkata has roughly 20 million or so. So Finland is 1/4 of one big city here in India. And in India you have now 1.4 billion, so 1,400 million persons. And so Finland is like a very tiny, let's call it a very tiny city, or not a village, but anywhere here. So we are very few persons in the big country. Which means that we have, on average, 60.5 persons per square kilometer. And in here, you have to be really on the countryside in order to reach this. And you might not even reach this low level. In your case, it will be 10, 100 times, maybe 100 times more than 100, 150 persons, or 50 times more persons we have. So the point is that our aim was, of course, to go from Delhi to Kolkata, as I said, short flight, 2 hour flight. So this was 2 hours, 1.5 hours, and this was 8 hour flight. So that's the idea. So it's a long distance, about 6,500 kilometers. In geographical, but of course with the normal flights it's easier to do. But this is now the map of Finland. This is actually the country. Now it's funded, so it's 1,500 kilometers long. And this part here is a border with Russia. So we have the longest European border with Russia. 1,300 kilometers long, or even longer. And the point in there is Finland is a long country, rather you can be narrow in that sense. And the place where I come from is here. And now, surprisingly, this part of Finland is called Central Finland. Although it's in the south. But if you look carefully, you can see the lower part of Finland and then the upper part of Finland. The upper part is Lapland. And that's why this part here is considered to be Central Finland. Although the whole country is called Finland. But former times, everything happened here. There's virtually nothing but reindeers in this Lapland area. But that's the idea. And this yellow point here is the Helsinki, the capital, where I started my flight. So I drove a car, 3 hours by car, 300 kilometers. And then the blue ones, what you see here, are lakes. So we have 188,000 lakes. So we have a lot of lakes. And we eat fish and all these kind of things, what you can easily imagine is coming. And also we have a lot of wild animals in the forests. But then one of the important things that I already discussed yesterday, look here, there is a Christmas tree here. And the reason is why there's a Christmas tree here is that the Americans stole Santa Claus. And then they tell that the Santa Claus lives in the North Pole and then flies with the reindeer. This is not true because the real Santa Claus is living in here. Everybody knows. And he is not flying, he just have a sledge with the reindeers. So he's not flying. So we are more realistic in that sense, but that's the idea. And the point out, there's a mountain, a small mountain. We don't have big hills or a mountain, and it has a specific name. Everybody in Finland knows that this Santa Claus is living in this specific mountain, and the mountain is called Ear Mountain. So the ear like this. And it's a real one. So it's in Finnish the same thing, so it means ear. But the point in there is that maybe that is the reason that it's considered that that's Ear Mountain because the Santa Claus is listening what is happening in there and then starts the journey in Christmas time. So that's the idea. But that's the part like a joke. But the point is that this is a typical picture of Finland in there, and you can see in May about one of the lakes here. We have a lot of islands there, and then there's a boat. Somebody's going to fishing. And this is a very typical thing what we have. The other extreme now, look, this is done more or less, I think it's around 11 o'clock in the evening. Because we are so far north that we have extremes with the sunlight. So in summer, there is no night. And in winter, there is no day. So if you go high enough, somewhere here in this region, the sun will go down and stay down for 3 months. It's not pitch black, but the sun, you can't see the sun. And then in winter, you can have something like this. So this is a forest with a lot of snow, frozen ice, of course, or water. And you can see this tree is very particular here because you can see it curves. So there is so much snow in the tree that it might crack the tree. This can happen. And this is the idea. And then you can't see very nicely, but there is a skiing track here, not skiing track here. So we are doing a lot of winter sports, of course. Ice hockey and skiing and this, because we have a lot of ice and snow. But now the global warming is really changing this thing a lot. And now when I left in Helsinki, it was +8 degrees. I started on Tuesday, which is completely abnormal. Normally we have -5. So we see temperature raise about 10 degrees now in the winter time. And in the summertime, we might easily go above 30. Because what we have here, Russia is a big continental area, so we can have a lot of continental air coming. But with this also, these are quite popular from Finland, but I think we might have also heard, and if you have a connection to YouTube, go and Google Northern Lights in Finland. Then you see something like this. And this is, why this is, you can have this in Lapland. The more north you go, the better you can see this. But these are really rare. So I am told my colleagues, they ask, you see northern lights every day. I said, no, I've seen 4 times in my life. Under 65 years, I've seen this 4 times. Because they are hiding. They are there at night, at midnight, 2 o'clock in the morning, and so on. It has to be clear skies, because they are, of course, beyond the clouds. If there's clouds, then you don't see anything. But this picture is taken by Rosie. Rosie is, surprising, by the way, an Indian postdoc in our department. And she took the picture at midnight, and why this is important, this shiny, a little bit shiny area, it's difficult for you to see, it's a lake. And this is a boat. And this is the Department of Chemistry. So our chemistry department is beside the lake, so you can come to the chemistry department by boat. Theoretically, you could come from here. It will take years, but in theory it's possible. But the point is, this is a typical color of the northern lights. We call it also aurora borealis. That's a Latin name for this, and it's green color. And the point in there is that these are actually changing. It's not like a static image. They are changing. They're moving around. And this year has been extraordinarily good for these things. I haven't seen them myself, but there's a lot of movies and videos about these moving northern lights in the YouTube. You just go to YouTube, and then northern lights in Finland, you will see a very spectacular thing, because they show all the colors, not only green. Green is a typical one, but all the colors you can see, from white to purple and bluish and all these things. So that's the idea, that after this lecturing and all this kind of, when we have a break, so you can ask me questions about also Finland if you are interested. But that's the, in a sense, the introduction where I come from, and now we start the real engines. So the idea now really is to go through and teach you a basic theory, basic facts, not mathematically, but on a conceptual sense about single crystal X-ray diffraction, what it means, what we can do with this. And I will have also a walkthrough here in this course. And I can provide you programs, and I can give you a link to the programs, what I use here in this course. And I can give you the data, I can give you the material for you to work by yourself, if you like. If you are a more experienced person, have done some of your work, and you have problems with this, you can ask me. So I can tutor you and help you on complicated things. But of course, in this course, we cannot go deeply on the complicated things. Remember, this course is for teaching somebody who has never done anything. Just really start from the basics and try to teach you what is there. You might have gone some courses yourself, but the point is, don't worry about this, because I will then cover these certain things from a different perspective. So, because the theory of X-ray diffraction is solid state physics. And you can describe that purely mathematically, but then you lose the real idea. Because as someone was saying, the idea that you can use computer programs. The computer programs are doing a lot of work for you. But the point, that's also the pitfall, because if it's too automatic, you might trust what the computer program is telling you, and this is not correct. Sometimes you have to be able to see that now the computer program is not able to see the real thing. And I will show you some of the pitfalls, which is a very typical thing, and I emphasize it many times, that the X-rays don't see the atoms. So X-rays don't know anything what is there. The only thing what they see is so-called electron density, and this is what you'll learn later on. And you have to, when you are doing the work, you have to tell these programs what are the atoms. And this is a big thing. This is sometimes you might make a mistake if you don't know. So doing a completely unknown structure by X-ray diffraction can be very complicated. Because the idea is that the X-rays don't see, for example, difference between a carbon and nitrogen. They look the same. And then it's up to you to think about, okay, now there are 4 bonds from this atom, and it's not charged, so it cannot be a nitrogen. It has to be a carbon. Because if it would be a nitrogen and you have 4 bonds going from there, it should be a cationic, and then you should have an anion. So there is a lot of chemical information you have to know in principle in order to understand what you see in X-ray diffraction. And this is just the idea of these kind of things. And the first talk, the first hour, is just introduction to the history of X-ray diffraction. When it was developed, who did it, what was the discoveries, and so on. And this is just this now. So the point in there is that this is actually a nice summary slide also, in that sense, because you can see pictures of crystals. You will learn how to look in the crystals, not with the microscope now in here, but theoretically. And then also learning about how to make the crystal, how to crystallize. This is a very important thing, because the X-ray diffraction is a very unique technique in a 2 ways, in a plus and minus. So the point in there is, when you manage to grow a single crystal, I will then teach you what is a single crystal. You manage to do a single crystal, then with a very high probability you will get the atomic resolution. You can locate all the atoms. But if you don't, you don't get anything. So if you are doing a mass spectrometry or NMR or any other analytics, you can run the experiment. But you cannot run the X-ray instrument. It's always a measurement, and only after the measurement, if it's good enough, you can have the result. And that's the reason we cannot ever promise in advance that we can get it done. So we have to do the work, and only after the work is done, we will see that, okay, what was the result? Is it what we expected, or is it something different? So we have to analyze. And this is also what I'm teaching here in this course, not only to do the work, actual work, but only analyze, look what you can get out of there. And it's a learning process. Nobody will be an expert after 1 course. When you have done 50 or 100 structures by yourself, then you start getting an idea, okay, what is going on? And that's the idea. So it's really a learning process. There's a lot of handwork what you have to do. But there are. So single crystal, diffraction pattern. This is what you see in the modern instruments nowadays. There is a MOF structure. Of course, we can study any kind of structures. So now the course, or the title in principle, says Supramolecular Crystallography. What it means actually means that we can apply crystallography to supramolecular structures. But the crystallography is always the same. It doesn't matter if it's a cough, MOF, or pharmaceutical, whatever, it doesn't count. So that is not the issue. The issue is the single crystal. Once we get the single crystal done, then we can do these things. And then here are instruments, pictures, there's a powder diffractometer, and different kinds of things. These are all things what you might see when you're doing the work. And then this clearly doesn't lock a single crystalline. And then what you have to do is try to figure it out, can I have single crystals out of this? Because if you can, then you might be able to get the structure. So because this handout, this is also available for you as a PDF. I will provide them through him. And there is some information about background materials. You don't have to go through this, but this is just information for you. There is a lot of these things with the simple books from Professor Clegg, and then a more complicated fundamentals of crystallography, which is here, which is really a heavy book. But you can see they are all 20-year-old roughly, so because the theory has been developed 100 years ago. And there is a list of these things, different kinds of things, the crystal structure analysis and so on. You can see this book, for example, is a very nice book, and it's from 72 and still absolutely valid. So the basic theory has not changed. So the way how we work have changed because the computers have developed. And that's the idea. So I will not go in details in here. But then you can also go, there are some websites. This is a collection, quite old collection. I think this is a 6 or 7 year old collection, but some of these things work. So you can go and click any of those and they will take you to the it's me, surprisingly. let's put it off. That you can go and see different things in the web, and there is a lot of, even if you go to Google and say X-ray crystallography, you will get a nice page on that. So the information is there, but the information doesn't help you if you don't understand what you're doing, and this is actually what we are doing in here. So I will list also the programs I will show you and use in this course. These are freely available programs for scientific use. They are called the Mercury. And then the Mercury is a freestanding program, but it's also associated with GIANxEFAML database, because this is also a very important tool for us. On any kind of a thing, MOF, GOF, Soft-Oxometalates, whatever, all these are stored, the X-ray structures are stored in the chemistry crystallography database. And it has now done in there, and now this is a little bit older, there is 1.4 million X-ray structures now. And we also go through in this course how we can look into the chemistry structure database and how we can study the structures is there. There is a homework which is associated with this course in my university, where the students have to do the search and see if the structure is known or not. And then OLEX2 is also a program set which is also freely available. We use these things, and don't worry about this. You don't have to worry about this. If you are interested on this, use these programs yourself, then I will then provide you. I have a link for these programs. It's a Dropbox folder, so it's available in there. And then the ShellX programs are the same. You might have heard ShellX programs, and this is a different set of programs which works inside OLEX2. So I like this OLEX2 program set because it's a very visual. It's easy to and I will have a walkthrough of the X-ray structure solution using these programs. But now really about the X-rays. So this is really a discovery what was done about 150 years ago by a German researcher. Actually, I think he was a doctor, Wilhelm Röntgen. And the point in there is that we have to go through a bit of the history where we come from, because the X-rays were not actually designed or discovered for that use from the beginning. So the idea is that he got a Nobel Prize in 1901 after the discovery of the extraordinary services returning with the discovery of remarkable rays subsequently named after him. Because the point, he realized that these rays will pass through material. And the point in there, what has happening is that you can create an image of a material based on this, depending on how dense it is. And this is actually the hand of Wilhelm Röntgen's wife. And this is the original image. You can see the idea, it's quite okay. You can see the bones. You don't see the muscles because they are penetrated by the X-rays. And then the ring. Actually, she has a ring here, so that is the ring. And now this is a higher resolution X-ray image of her hand. And you can see the idea that how the joints are there visible. So now you can easily understand that now you can look inside a person. And when you're looking inside a person, you can see if everything is okay or not. So this is, of course, used to look for bones. If you have a broken hand or bone, it's visible in X-rays. But that's the idea. This is the idea. But we don't, of course, use X-rays in this way. So the next person who is associated with this thing is Albert Einstein, about the quantum theory of light, because now X-rays is a part of light. And now we have to know the behavior of the X-rays, meaning light, and how it behaves, how it interacts with the matter. And that's the idea of, we consider of photons were associated. And the point is that the photons are tiny packets of energy, which has a characteristic both particle and wave. So now our work is better understood if we consider the light as wave, because all what we do this, we describe this as a wave. This is the easier. We speak about wavelength. And that's an important issue in our case for this. And that's the idea. So he then coined, of course, the famous E-mc squared based on that. But that's the idea. So we disregard the particle nature of the way we look that as a wave, or light. We look that as a wave. And that's the idea. He got the Nobel Prize in 21 on this theoretical physics, the discovery of law of photoelectronic effects. So that's part of the phenomenon of light. But what is important in a wave, or light in general, is a wavelength and amplitude. And these are the important points, what we need to know. We don't have to really understand the basic physics in here. For our purposes, the wavelength and the intensity, the amplitude, is important. There is one feature which exists with the light, which is the most complicated thing for us. It is the phase of the light. But I will come to that later on, because without the information about phase, so knowing where the maxima and minima are, is important. But then in 1912, Max von Laue and Friedrich and Nipping, they did an experiment of continuous X-rays, all wavelength, through a crystal of copper, sulfate, and zinc plate, and realized that now something is happening. So they didn't now make an image of it. They realized that X-rays will diffract. So they bounce from this crystal. Something inside the crystal is bouncing the X-rays, and that is the thing what they discovered. And this is what happened. So this is the first diffraction image. Diffraction meaning now it's the same as wave or light is bouncing from mirror. So that is, we can call it diffraction. Then it's because diffraction is in principle the same as reflection, but diffraction is because it will have to interact with the material in order to do this diffraction. And later you will learn where this diffraction comes from. But that's the idea. And then the idea of crystals are decomposed periodic array of atoms and cause distinct X-ray diffraction patterns due to the atoms and their three-dimensional spacing. This is now the first really important information. So now, if you read this reversed, it means that if we know these points, we know this point's position and we know the intensity, we can in principle follow back to the crystal on that point where the diffraction happens. So we can actually follow the light reversed on the spot, on the position where the diffraction happens. And this is actually what we are doing. There is a lot of complications how to do this. It's not a very simple thing to do, but luckily the theory of this has been developed already more than 100 years ago, so we don't have to worry about this. But this is the idea. So they received a Nobel Prize in 2014 on their discovery of diffraction of X-rays by crystals. But now there is no real structure. It was really information that now there has to be a periodical order of things. And that's the idea. So then really 1 year later, or 1913, there was their father and son, Bragg, who actually were building up an instrument. The instrument is here now. What they did, they shined light on a crystal and then used a detector here to do it. So this was really like, looks a little bit like our diffractometer, but now it was not monochromatic, so the continuous X-rays. And now these guys, both guys, were studying the phenomena, what is happening, and they found out that there is a law. There is a certain regularity which is filled up by a very simple law. And this law was then later named as Bragg's law. And the Bragg's law is a very simple thing to do. But there is a lot of things in there. So now consider these points. For you, it's easy to, let's say, understand these points as an atom. So let's consider that the blue is an atom. And now when you look for this atom, take any atom here. When you see its neighbors, they are always the same distance away from this point. So in this kind of a thing, we have a periodic system where we can think about that there is one layer of these atoms here, and the second layer in here, third, and so on. And now when the X-rays are going and hitting in here, they will hit the electrons of the atoms. We will see that later on. So it is, and they bounce off, diffract from here, and they diffract following this law. So now the wavelength, the multiplicity of the wavelength, normally n, we always consider n as 1. So it means just the wavelength is proportional to the distance of these bouncing is happening with the angle where the diffraction is happening. So why this is important is that when we know the lambda, the wavelength, this becomes constant. We know we can measure the angle. So with the instrument, we can measure the angle. Then this becomes known. The only thing which is unknown now is the d, and we can easily calculate. So this law actually tells us a lot of information from which kind of order the diffraction is coming from. And this is the essence of all diffraction. And we have to follow, we have to try to figure it out how we can use this in our measurement. And this is really the idea. And now the Braggs actually got the Nobel Prize for the next one. They showed that they can use this diffraction pattern to determine relative positions of atoms. Because I go back, so the point in here, there is no real, that's the Bragg's law, that there is no real structure, it's just ordered. But now consider that you have real atoms or real molecules in there. If they are ordered in the same way and they can diffract X-rays, you can actually then determine the structure. And this is what they did. So they showed that diffraction pattern can be determined, the relative positions of atoms, within a single crystal. So I will always emphasize single crystal. And the single crystal means two things. It has to be a single entity which is perfectly ordered. Because if it's not, then you will not get a unified or clear diffraction pattern. And then the Bragg's law doesn't apply. So in order that the Bragg's law is applied, you need to have a periodical ordered structure in 3 dimensions without errors and anything like this. And this is the most complicated thing to do, to get the single crystal. As I told you in the beginning, if you can crystallize any material in a nice single crystal, it's very likely that we can get the structure solved and then see what we have. But if there is an even tiny errors in there, then the mathematics don't work anymore. And then there is no help. You cannot make something happen if it's not there. That's the idea. It's like multiplying 0 with any number is 0. It's the same thing. But that is the idea. So they got the Nobel Prize in 1915 with the services of analysis of crystal structure by the means of X-rays. So this was actually the starting point, and now it's 120 years ago and everything done. So we are dealing with a very old thing. But it's interesting that with this very old thing, we can measure and do research on a brand new unknown systems. So then 16, they developed a different technique. It's called powder diffraction. In this course, I will not consider powder diffraction. It's a special case of a single crystal, but there are a couple of slides showing this, but I will not really go in detail. But the point difference in here is that you will not anymore get a single diffraction pattern as you saw previously. You get, because there is a mixture of different crystals, you will get lines. You get a diffraction pattern, that the diffraction pattern doesn't look the same as from the single crystal. But it's very handy and it's very practical. And these guys, Debye and Serre, Debye got the Nobel Prize on the contribution for knowledge, molecular structure through investigation, dipole moments, diffraction, X-rays, and electron gases. So these guys developed these things, and now you can see that the Nobel Prize is now coming more on applying the X-rays. But these guys, and this is a very simplistic cartoon of a powder diffractometer. This is what it comes from there. And then in 1917, this person here developed a very important concept on crystallography, because it's very heavy on mathematics. Mathematics is quite complex, but there's a lot of numbers. The mathematics itself, it's not very complicated, but it's a lot of calculus what has to be done. But he actually describe the interaction between the waves with the regular lattice, what we have. So we call this ordered structure a lattice. So he was able to describe this, and then he was developing the theory of this, and then the idea is that he was able to describe a mathematical treatment where the diffraction patterns can be mathematically related directly to the individual diffractions. You will learn that later on, and this is called the reciprocal space. That is a rather complex mathematical concept. I will not go into detail in this, but we will use it, and the computer programs are using this all the time. So he developed this kind of a thing in there. And Serre was using X-rays to determine the crystallite size. So now we can apply X-rays also not having the structure, we can having the crystallite size. So we can say, okay, what is the size of the crystallites? Of course, then it has to be a powder. So this is a powder method. And the idea, it works like this. So this is a powder pattern. And now the half height of this peak corresponds to the crystallite size. So it can be used in material science to look for crystallite sizes. And that's the simple idea. And then 21, roughly 10 years later, the previous one, Bragg was solved a structure of organic structures. So the organic structure is much more complicated because all the other structures were three-dimensional, like sodium chloride. But now if you have a molecule, the molecule has to organize itself in a regular pattern. And this is much more complicated, of course, because it means that you have to grow the crystal. And these are the first X-ray structures of anthracene and naphthalene for that. And this is actually the result, what you can get from the diffraction image. So these are the electron densities of that. So we don't see that this is carbon or nitrogen. We see just like a small hill. And what we do, we are looking for this kind of a thing and see what is that. But that is the idea. You can see clearly 3 rings here, and there are 2 rings here. But that's not for 100 years ago. And it took months to do this. Now, probably I will show you a video later on, maybe in the final lecture course, where the modern computer programs and diffractometers can make a data collection and solve the structure with an optically pure molecule in 90 seconds. Because everything is done by the computer. So there are extremely powerful computations between that. Now, there are some pictures of Weissenberg camera and all the other powder diffractometer and also Weissenberg camera. This is just the idea, development of Weissenberg camera, where Weissenberg and quickly routinely made a diffraction experiment, because you have to record it. You have to record the diffraction pattern, and this is made by films at that time. But then you have to read the film, and it was really complicated to do this kind of thing. And this is just a principal cartoons and pictures about this. It looks like this, mechanical instrument, and the film is there, the X-rays are here, they are hitting for the crystal, and then they make this kind of a diffraction pattern. And these diffraction patterns can be then mathematically treated by hand at that time to see where the diffraction is coming from, so meaning the crystal. And then the next step for your was precision camera, which is in principle modulation of the Weissenberg. And the idea is here that now you get this kind of a thing because this is able to rotate the crystal differently. And we get a diffraction image looking like this. Is like a night sky with stars, but the stars are black and the sky is white. So it's like reverse negative kind of a thing. But now this information here can be converted to mathematically to the structures, and this is what we will do, or the computer programs will be doing. And now we will make a big jump. So there was virtually nothing happening for 30, 40 years. Technology, because these were all mechanical instruments, the previous ones. But now in the 70s, the computers were developing, and then robots, meaning moving instruments, which could be programmed by a computer program to do movement. And this is now essence for our business. So if we can give the robot or the instrument to do the measurement by itself, we don't have to do it manually by clicking 1 and 1 and 1 and 1 and then recording that. So in the 70s, we started having the commercial diffractometers. So you can buy an instrument, and the instrument is called diffractometer. Even that in the 70s, it took from 1.5 to 2 years to get an X-ray structure. But then the point is that this, when everything develops, we can get it faster. Still the basics are the same. So everything is the same, only it's speeding up these things. So that is the idea. So we have here a picture of our instrument from the 70s. This is called the 4-circle diffractometer, and that's the crystal is sitting here. You can see it moves like this. And this was the big breakthrough for this. These are just images of these things. So this is so-called full-circle diffractometer, and this is so-called kappa geometry for this. So it's different geometry, how to control the movement of the crystal. Because what we have to do is still shoot X-rays, and this is a sample holder. It's called the goniometer head. So our sample is here sitting on top of it. So you always consider, okay, what is crystal? You can consider microscopic size, like the size of this crystal, but in real life, it's really tiny. It's so small that we have to work with the microscope with it. But that was the idea. So in the late 70s, this started coming. But in the late 70s, we have these 2 versions of coming. And the point in there is that we started having detectors. So in here, for example, in this case, here is the detector, and this detector is able to read 1 reflection at a time, not more than that. And then this was like, I started my work in the mid-80s. So our instrument, what we had at that time, was from the late 1970s. So it looked like this, the instrument. And it was really tedious to work. There are no computers, no personal computers, nothing like this. You have to do a lot of computer science, or you have to do calculations in a mainframe computer in a computing center, and so on and so on. It was really tedious kind of a thing. But that's the idea. And then in the 1990s, it's further development. The instruments getting more and more powerful. They were more and more automatic. And one of the big things were there that a new detector type was discovered or taking into use. This is called the area detector. So now it doesn't record 1 diffraction image at a time. It was recording hundreds. And that's the idea. So that is the idea we call the CCD detectors. And they look like this. So this is actually a picture of our old instrument. We had this big detector, this kind of, it was 15, 16 centimeters in diameter. And then it could be able to record thousands of spots at the same time, or hundreds, let's call it hundreds. And now, further development, more speed, more range for the detectors, and so on and so on. And now we start to see large structures, because prior to 1980s or mid-80s, doing a supramolecular larger structure with more than 100 atoms was no can do. But now, in the late 90s and early 2000, the instruments became so powerful that you can do this kind of a thing and start doing. So that was actually the start of supramolecular crystallography, so meaning crystallography of supramolecular structures. And I was lucky in there to follow the development of the instrumentation from these simple ones to more sophisticated ones. And now, even now, there is still development going on, and development is going from the way how we do the X-rays, how we create the X-rays, and how we record them. And now, then this was large supramolecular structure, took maybe 1 or 2 months in the early 2000s. Here it would be, let's say, a day, 1 day or something like this. Still takes 1 day. At 2 or 15 years ago. But then, of course, you know that there is a very powerful system called synchrotron radiation, but these are big facilities. For example, our country doesn't have any. Nordic countries has only one, but for example, England has a few of them. One is the most well-known is our diamond light source, but you can have, this is in Grenoble in France is one, and this is in Barcelona. And the point in there is that you can change the wavelength from microwaves to hard X-rays, so you can tune it. You can do a lot of things with this. But these are extremely expensive to do this. So no normal country even has this. You have to be a rich country in order to have synchrotron. And I've never actually worked on a synchrotron myself. I've used data from synchrotron, because when you get the data from the synchrotron, it's same as you get the data from your own instrument. So the mathematics and everything is the same. It doesn't matter. But it's extremely powerful thing. And it's so intense that actually it explodes the crystal. So the point is, when you shoot X-rays and there's singular radiation, in 1 second it will record everything and it explodes the crystal. But the detectors are so fast that they can actually really measure everything, all the information. And that's the idea. But using a synchrotron is a very special case, but it can be done also with powder. This is known thing. So now this is the pictures of our instruments, what we have. We have 2 instruments. And this is the newest one. So this is called the regardless energy R, which is rotating anode here. That's the detector. And now, if you look carefully, the detector is curved. And this is a really nice new invention, that you make a curved detector, because it speeds up things a lot. And then this is the goniometer. This is the robot which moves. The sample is there, and that's a cooling device. And this is kind of a thing. There are some cooling systems in here, but it's self-containing. And the power, what this is doing, is 1.2 kilowatts, but it's extremely powerful instrument. And this is actually designed and by the company, designed for protein work. So you can do protein crystallography at home with this instrument. We are not doing that protein work. We are using the instrument for a normal work, what we are doing. And then this is the old version of the same instrument, but in here we have 2 radiations. We have a copper and moly radiation. Here is only copper radiation, because the wavelength makes a difference. So wavelength has a meaning for that. But now you can see the detector here and the detector there is the same, because we were able to upgrade on this old instrument. We were able to upgrade the detector. So this instrument became 5 times more powerful only by exchanging the detector. And now the power difference between these two is about 50-fold. So if something takes 50 hours in here, it takes 1 hour in this instrument. So we can easily do 10 structures a day with this instrument without problem. So that is now where we are going and currently, but this is the actual idea. And then what has been done? This is the closing. Soon we'll close the first hour. History of X-ray diffraction. So the achievements, what has been achieved by X-rays. And this also involves a lot of Nobel Prizes for this, because it's a very unique. So in 27, this person here proved the structure of benzene being a planar. So before that, you didn't know that the benzene was planar structure. There were hints and theories about this, but nobody was able to show experimentally. And experimentally it was done by Catherine Langtais. And here it is. That's the benzene thing. And then in 72 and 32, Robertson solved the phthalocyanine. So now we are going already more on the bio-related things, the bigger structures. And then 42, Roy Hodgins solved the structure of collagen diide. Then she got the Nobel Prize on X-ray technique of important biochemical substances. So now X-rays are being applied to study something important, biological or whatever. And that is now a material science, supramolecular chemistry, biochemistry, medicine, and so on and so on. So it's a technique which is applied for this. But the point is, this time there were no computers and so on. All the calculations had to be done by hand. This is what I will show you in the beginning. So this kind of work took years. Very tedious work. 42, this person here Sumner, got the Nobel Prize demonstrating that proteins can be crystallized. So he got the Nobel Prize on the crystallizing proteins, not solving the protein structures yet. Because before that, nobody realized that protein can be crystallized. So there is a lot of also learning techniques how to handle the material to become a single crystal. Because of course, what it means that when you say that the proteins are crystallized, there has to be single crystalline. And then in 48, a new journal was created and still exists. It's called Acta Crystallographica, but this is the launched crystallography journal. It still exists in there. And then this is the famous Watson and Crick. They used X-ray diffraction to deduce that the DNA is a double helix. And that is the idea. So X-rays give a huge amount of information on the material, what you have, provided that it's crystalline. You have to emphasize this, that if your system is non-crystalline, you will get nothing. That's the point. And then in 57, vitamin B12 was determined. And then in first globular proteins, there are 62, the Nobel Prize was given to Kendro and Perus for the studies of globular proteins. That was the, and it is 60 years ago. And then the idea is surprising that this development was really fast because this was related to the crystallizing of these materials. And now still there is hundreds of thousands protein structures only, not millions. And that is the point. So because the more complex they go, the more difficult it is to crystallize them. And Bragg solved the lysozyme, the bigger one, and then 82. Aaron Clark got the electron microscopy crystallographic work on that, so you can use also electron diffraction for this. And then in 85, actually I was in the crystallographic meeting when this Nobel Prize was launched by Hapman and Karl about a mathematical treatment, how to solve a structure. And you will do it and learn it also during this course, how to do this. But the mathematics, how to do this was developed and put into a computer program by these two guys. So they developed the mathematics, how to do this. And now we don't have to worry about the mathematics anymore. It works very well. That's the idea. And it's only about 40 years ago when this was done. And this also relates to the development of computers. And this direct methods, this is the idea for the outstanding direct methods. Direct methods now, it's the phase problem. Remember from the beginning, I told you that when we have a wave, we know the amplitude and the wavelength. But the thing we don't know, which is impossible to measure in a certain sense, is the wave, the phase of this. So where is the minima and maxima occurring? Because it can change. It can be different from different waves. And in order to do this, we have to know the phase. In principle, you can consider the phase is a number. So we have to know if the number is 90 or 95 or 110 or so. We have to know it because without this, the mathematics don't work. And these guys, when they were doing this, they managed to create a mathematical treatment on the diffraction data. So the data knows this. So data contains information about this, but you cannot see directly. So they developed a mathematical treatment how to do this. And now this is embedded in all the existing programs. And they are really powerful. So you actually don't realize what is happening inside there. There is a lot of happening in there. But this is the idea of how it was developed, and it's only 40 years old. And now if you would have a very slow computer, it will take a long time to do this. But nowadays the computers are so powerful that this thing takes a second or two. So the mathematical treatment of these things. And then they are so powerful because what these direct methods are doing, they will give a guess of the phase. They are trying to figure out what is the phase of this reflection and diffracted beam. And then when you have it, they will give the number and then see what happens. Because later on in the course, you'll realize why it's needed for the mathematics. And now I think that is my final slide in this introduction, just to go on in there. What is now the state of the art, more or less? So what you can do with singular, so you can get 100,000 or more atoms in there. And now, what is there? You can see the resolution. You will learn later on what is the resolution. But the resolution here at 2.4 angstroms, it actually sees the amino acids. It doesn't see the individual atoms. But later on in the course, you will learn where does this resolution come from. But the point in there is that it's 25 nanometers in diameter. So these are absolutely outstandingly huge systems. And before that, let's say 15 years ago or so, it was considered impossible. But now you can even crystallize a virus, and you can get the X-ray structure of a virus. And this is, of course, huge impact for medicine and also studies of this, what is happening in there. But that's the idea. And this is actually how the protein looks like when you're showing the surface of the protein, because of course the atoms are not balls, how we normally show them. Ball and stick model is not the real one. They're more like spheres joined together, and then you create the surface of this kind. And then, for example, drug molecule might go in this hole here and have an impact on what is happening. So this is the information what we can get out of it. And I think that was my final slide for this. And now if you have any questions, so now it's 1 o'clock already. If you have any questions concerning this, you can ask now. We have a short break now for 5-10 minutes. What is the normal thing? 5 minutes is fine. Okay. Let's do this. And the material will be available. You will get the PDF for these handouts. So you don't have to, you can make notes, and of course you can do. But the point in there, I will then provide you, if there's an email address for all of you, then I will be able to provide you the PDFs for all of these. They're quite big, some of them, but I will manage how to do this. Okay, now then is the 5-minute break.
Hello, sir.
Yes?
Sir, the larvae generally did the XRD in the real space. So what is the need of the reciprocal space there?
That's the mathematical treatment. You will learn it later on, because the point in there is that how the diffraction, okay, we are now going, this will be explained later, but anyway, you can consider the diffraction happens from a plane. Remember this kind of a thing, like a mirror. The mathematical treatment, the reciprocal rate, transforms the plane into a point. And this point is actually what we are measuring. So later on, you will see a diffraction pattern. And the diffraction pattern is actually the reciprocal presentation of the orientation of information inside a crystal. But we are too early to give the answer, because you will learn it later on where this comes from. Okay? Any other?
Sir, one more question.
Yes.
That why the synchrotrons you have mentioned?
Yeah.
The synchrotrons, how they create the more high-speed X-rays?
Yeah, because the point in there is that what is happening here, they circulate the particles. This is the synchrotron, and then these are hitting with a very high speed to an anode. You will see that next lecture will be about X-rays, how they are made. And it comes from the speed of the electron when it hits the anode, and that makes the power. So that's the idea. So that's why they are 1 kilometer in size. And then
the speed also gives them more.
Yes, that's the momentum what is there. So that is the actual idea why it's so powerful. So brightness is about 1 million times more than we normally have.
Okay, sir.
Okay? Okay, now the 5-minute break. Thank you. Okay. Now I took my jacket out, but it gets too warm in here because let's see how it goes. Now, start the engines. Okay, now. Oh, sorry, not this one. This one. So the idea now for this second lecture, 1 hour or so, is now to describe the X-rays. Remember, very briefly, it showed you where this has come from, where the Bragg's law and all these kind are there. But now, how to make what are X-rays? How we can make it? What is the instrument? What is the important thing? Why we need X-rays? Because the core is called X-ray crystallography. It means we need X-rays. Why do we need X-rays? That is the first question. Why do we need? Why can't we use microscope? Why can't we do things? And that's the essence for this. So now, in principle or in practice, X-rays are electromagnetic radiation. You already saw this thing, that we have a wave, and wave have a direction, of course, and the wavelength. Wavelength is measured between these two maxima there. And then we have the intensity, the amplitude of this thing. So the higher is this amplitude, the stronger is the radiation. And then it has two major things, the wavelength and the amplitude for this. And you can easily do. But now you can see here, when description of the wave, the phase is needed. And this is really the essence. This we cannot know. It's impossible for the technique to do this. Amplitude, we can measure, we can do the frequency, and we can look for this wavelength is known. These two are like known things, but the phase is not. And that was the direct methods development for mathematical treatment is there to help to solve the structure. Without that, it gets very complicated. There are methods to do this, but nowadays, in order to computer programs to do this, that was a big thing in there. But the point in there is that we can consider the electromagnetic radiation to be considered particles called photons, and the photons is associated with energy. But point in there, it is true, that's the case. But in our case, it's easier to try to understand the X-rays based on the wave formulation. And I particularly like this slide because this will tell us why we need X-rays. So X-rays is the wavelength, certain wavelength light, and that's the idea. But now, here we have the length scale in meters. So you can see here 10 to the power of 3 meters and 10 to the power of minus 12 meters. And now the idea is that what is there for our purposes? So you can consider that here we have objects, real objects. And the idea is that if we take a soccer field, the scale or the wavelength size in order to image a soccer field would be 10 to the power of 2. So with the 10 to the power of 2 radiation wavelength, we would be able to see the soccer field. And then if we go one step down, we go 10 to the power of 1, so we can see a house. And now the idea is that if we want to see a baseball, we should use a wavelength radiation of 10 to the power of minus 1 meters. And now you can see what happened. The smaller is this. So this point, when you print it out, is 10 to the power of minus 3. So we are actually seeing things in there with the visible light, which means that this is our maximum thing what we can see with the light. With your own eyes, it's very difficult to see a cell. It has to be a big one. But with the microscope, which is using visible light, that's possible. Because we know now that the visible light wavelength is somewhere 10 to the power of minus 6 and minus 7 between there, something like this. So 500, 300 to 800 nanometers, we speak in nanometers. But we like to use the meter scale because it will lead us to a very useful definition of length, what we can use in single crystal X-ray diffraction. The point in there is, okay, in order to see a virus, we would need a wavelength to the 10 to the power of 7. Now, with a protein, we would need 10 to the power of -8 or 9.5. But now, if we want to see a molecule, we are now in here in this magic 10 to the 10. And the point in there is now a very nice description for this 10 to the -10. It's called Ångström. And this Ångström length scale is absolutely perfect because this is the length scale of an atom distances. So in order us to see a molecule, we need to have X-rays. So only the wavelength of this X-rays is so small that we can separate these entities. And that's why we have to use X-rays. We can't use anything else because if the wavelength is longer, we can't separate the objects. We can't see. And that is the resolution for proteins. So the resolution in the protein X-ray structure is lower. So the wavelength is the same, but the resolution is lower because we can't see individual atoms. We can see amino acids, but we want to see individual atoms, and we have to use wavelength which is on this range. And you can see now what are the names for this. So radio waves are here, microwaves, and so on, ultraviolet, and hard X-rays, soft X-rays. We are here on that region. This is what we have to make them, the X-rays. They don't exist naturally, like visible light exists. So we have to make them. And here is how we make the radiation. And we start from there. So we have here a radio waves. So that's the idea. And then we will go to microwave oven. In theory, with the microwave oven, that's a joke, you could separate this baseball. But of course, you don't do this. But it's just the idea that, okay, then radar works here. People are in this scale. And then light bulb is here on the visible light gate, like we have here now. Lights, they are all producing now a wavelength of this. And then X-rays, we can have a synchrotron, or here the robot like looking X-ray machine, because it is actually a robot. And the actual, we have to do this. And the point is that X-rays are high energy, highly penetrative electromagnetic radiation and wavelength range. So this is where we are, where we have to be in order to see atoms. And the other, if you consider in here in the lower part, visible light range is from 4,000 to 7,000 Ångstroms. And we are now speaking about 1 or 2 Ångstroms. So the visible light is about 4,000 to 7,000 times too long for us to see the atoms. And this is what we have to do. And now how the X-rays are created. So regardless of the material we have, they are always created in the same way. So what happens here, so we have our atomic nucleus, and the atomic nucleus has electrons in the K, M, and L shell. And what we do, we shoot electrons into the atom. And now when the electron now here comes, it can do several things. So I will put all these things. So events 1, 2, and 3 interact with the vicinity of our nucleus, resulting radiation, produce cause, degradation, momentum, blah, blah, blah. These things are not okay for us. So this creates coherent radiation. So this creates, and so on, and low energy, maximum energy, and so on. But the point in there is that the process, our dominant long applied voltage, is insufficient to remove electrons from the nucleus. So what we have to do, we have to shoot the nucleus so strongly that the electron jumps. So either you can consider that it jumps to the next shell or it completely goes out. So there will be a hole. And the hole is not permanent, like this in here. So what this wants to do, it wants to return back. It wants to fill up the hole. So we have a hole here in the K shell, then there from the L shell, the electron wants to return back. And when it returns back, it will emit radiation. And this is the X-rays. So when we reach a high enough voltage for this, meaning their speed of the electrons to hit the nucleus, we can see this phenomenon. And now depending on if we kick it hard or harder, so we can kick it also from the K to M or K to L. And now when it returns from here, L to K or M to K, it will create a different kind of X-rays. And that's the idea. And regardless of the element where we are using, so we are using a certain, typically it's a tungsten electrode, a cathode, where we take the electrons and we speed them up with the high electric field to hit the target anode, which is this thing. And inside this anode, we just kick the electron out and wait that it will return back and emit the X-rays. And there is an important point in here. So if the voltage, so the speed of the electrons is not high enough, there is no X-rays. So we need to do this because the idea we need that thing to happen. And that is the idea of what happens in here. The characteristic radiation emission, where the incident electron, the energy greater than the occasional bond, collides with it and ejects. And now the electron shell transfers this. It emits then. This is now the characteristic discrete energy packet which released from this. And this now appears to us as, as X-rays. And the point now why, even though the phenomena is always the same, now the target is important. So the point is, what is the type of the atom? What is the element we are using to create the X-rays will have an impact on what is the wavelength of this radiation created. And we can do this. So it's a very simple thing to do. So the point in now is the characteristic peak, which is called the K, L, and M, and they correspond to transition, of course. And the transition difference now reflects the energy which is transmitted in the form of X-rays. And the point where the two orbitals involve the adjacent cells, the line is called alpha radiation. And now, if it's separated by another cell, it's called the beta radiation. So this is the idea. These are the two characteristic things. And the point in there is that this is, I like this image. Hopefully you can see this nicely. So here you can see one spectrum, second, third, fourth, and so on, with the different voltages. So now you can see that this is this kind of a flat spectrum which comes in here now, unless you hit 25. When the voltage reaches 25, these peaks will appear. So these two. So these are the characteristic X-ray radiations which are coming in there. And this is the whole spectrum. And you can see what happens. There are two spikes. Two very strong spikes are coming out of there, which now reflect the energy between the two cells which are there. Either it's alpha or beta. Beta typically is lower in energy. Alpha is slightly higher, but you can see now, depending on which cell it goes, we can have an alpha 1 and alpha 2 for this kind of a thing. But now, this is very difficult to separate. So we consider that this is like a 1 radiation, and this beta is there. The point in there is we cannot use the whole spectrum. Because now, remember, if you remember the Bragg's law indicated the wavelength. And the wavelength was one number. So we cannot use a continuous wavelength in there because we would get a blur. So what we have to use is either one of them. So either this K alpha wavelength or this one. So this is nice because we can easily measure them. We know what is the wavelength for this. And now the idea is that if our anode material, so meaning the material where we shoot the electrons and then it releases the X-rays, if that is molybdenum, we get two alpha radiation, K alpha 1 and K alpha 2, but we always use the average, weighted average of this, and it's 0.71073 Ohmstroms. This is now a very important, this is an Ohmstrom scale, what we are using. And the point in there, this is always what you import when you report when you're using molybdenum radiation. But you can change the anode material and you can take a copper, and now you can see what is the difference. Now the copper radiation, the wavelength is 2 times longer. It has an impact, what is happening. Later on you will see what is the impact of the change of the radiation. And then we can have an iron also. The iron is even longer than copper, so we can change. Silver is shorter than molybdenum radiation. So what means that if we are able to treat our instrument and change this anode material, we can change the wavelength. But remember, with one experiment, we use only one wavelength. So we have to do this thing. We have to select, are we using this wavelength, the molybdenium wavelength, or are we using copper, which are the normal ones? So molybdenium, copper are the things we use. We cannot use both of them simultaneously. We can repeat the same experiment with copper radiation and with molybdenium radiation, but the result will be the same. The only thing is there that the interaction of these wavelength, the radiations with our crystal might be slightly different. So the longer is the wavelength, the more it will be absorbed by the crystal. So the copper radiation is typically more absorbed than moly. So molybdenium radiation is therefore used in inorganic compounds, and organic compounds and proteins are then studied with copper radiation. But in principle, there aren't any fundamental differences. The only difference is that this peak is in a different position. But that's the idea. This is the easiest way to do it. So what we do now, we have to, and it will be in the next slide, we have to have a measurement, we have to have our instrument or method to remove this background here and this peak and this here. So we want to keep only this one. And this we'll call monochromatic radiation. Monochromatic means single wavelength. In here we have agreed to use, because these are so close that that's actually not the problem for us. So we can use the average of here. But this we call monochromatic, so we have to use only one. And now we are happy with the Bragg's law, because the Bragg law has now a number, one number only. And that's the idea why we can use this. So that's the idea. And what is the speed we need to get this thing done so that we can see the characteristics X-rays is between 10 to 100 kV. Typically it's 50. Between 40 to 50 kV is needed. And then we use a power, and you can see the power is much less. When you combine these two, you can get maybe 1,000 watts or so. That's the power we use to create X-rays. But there are different methods, and the question about the synchrotron is that the synchrotron in principle is the same thing, but the speed which is used, I think it's a giga-electron volts or something like that. So it's so huge, the speed of these electrons, that it creates extremely powerful X-rays. But in principle, it's the same thing. But you need to have a certain minimum number for this voltage in order to do this. And the point in the modern powder instruments, they are even done so that you can separate alpha and beta. So in alpha 1 and alpha 2, because in powder diffraction, it might make a sense. But in single crystal, we can merge them into one diffraction spot, so it doesn't matter for us. There is no, we don't gain anything by separating these things, so we just use it as they are. And that's just simple mathematics. I will not go too much in there, but this is the description for this, all these. And there is the actual idea for us to understand that we need a certain minimum voltage in order to create the characteristics X-rays, and then we have to have another means to separate the unwanted radiation from those what we need. And this is, again, very simple. It looks, okay, there's a lot of things, mathematics and so on and so on, but actually it's a very simple thing because we just need a device to do this. And the device, how you make X-rays, is an old invention. It's about 100 years old. And the point in there is that we have different types of how to make X-rays. This is a quite nice cartoon way of doing. So it's like a glass tube. And inside this glass tube, we have a cathode. This is typically tungsten or something like that. When you heat it up, when you heat this up inside the vacuum, you release electrons. And now what you do, you create a voltage between this part and that part. So then it means that now the electrons which are removed from this tungsten wire will start to rush into this anode. And now they hit the anode, as we showed previously. they kick out the electron, returns back, and now the X-rays are coming more or less 90-degree angle from the anode. So the X-rays are not coming out from here, it's coming from the side. So this is a technological thing we have to take into account. So our radiation source is always perpendicular to the creation of the X-rays. It's a very nice thing, and it's about, here we have a picture of it. So this is about 25 centimeters times 10 centimeters, weighs about 3 kilograms, 4 kilograms. In my course, I always show one. I have one old tube so everybody can see how it's there. And this is now the cartoon of this. And now you can see that the X-rays are created in this direction, but they come out in sideways. And now they have to come out from this glass tube. So how do we do that? So the one thing, and what is done, is that we have small windows here. So actually, it's difficult to see, but maybe there is a window in here now, a round window. And the round window is made from beryllium metal, because beryllium metal doesn't absorb X-rays. So it's like a window, but you cannot use normal window. So you have to use beryllium for this. It doesn't absorb X-rays at all. But the only difficult thing with beryllium is that it's poisonous metal. So you should not touch this beryllium windows with your hands. But it's okay. But that's the idea. This is what we call traditional glass X-ray tube. And this is really about roughly the size of this, but a little bit bigger than this. And you can buy it from the shop. And the price is something like 5,000 euros, so it would be like 50,000 rupees. Am I correct? 5,000 is, no, it's 500,000. Yeah. 500,000 rupees, or 5,000 euros. So relatively expensive piece of thing. And now the X-rays are coming in there. And then we have also, this is called the stationary anode X-ray tube. And normally the power of here is around 2 kilowatts. And for that reason, you can see the idea that there is a water cooling here. So in this part here, it will melt more or less immediately if you don't cool it down. So you need the water circulation, cooling in here. And it's quite a lot. So 2 kilowatts, so 2,000 watts in a very small compact space will heat a lot. It will melt if it's not being cooled down. And then the current new systems where we're using this, they are controlling this, and if the water circulation stops, it will shut down the instrument, because it might then explode the thing. But when there is no power, there is no radiation. So the X-ray tube itself is safe. It only makes X-rays when we have the power on, when we're shooting electrons in there. And now what we can do, we can change the anode I told you earlier on. So this is the anode, which is creating the X-rays. So typical what we have is a moly, copper, iron, cobalt, chromium, or silver. Other things are also possible. The idea is that then there is a new method called liquid gallium anode, but it's a very special thing. It's like a wild horse, but in principle theory is the same. But the point is, it needs a water-cooled to remove excess heat. And that is the idea. And then you can see here the price, roughly 5,000 to 6,000 euros each. And it lasts between 5 to 6 years. So that's the running cost. So the instruments are quite costly to run in that sense. So this was invented more than 100 years ago. Of course, that's the idea. And the point is that it's still the most used one, because it's a very simple one. And many of their simpler instruments are using this because it's like a plug and play. You just take it out, put it back, and then you tune it a bit, and that's that. So it's a very handy to use. But the point, of course, you need electronics to create this high power, and there's a potential in there. But in principle, it's a very easy and old invention for this. This is called the old X-ray tube. But then there is another version of this tube, which is in principle it's the same. But now the previous one realized that the anode was stationary. The anode was sitting in one point, and the electrons were shot into it. But now the rotating anode name describes you that now the anode is rotated. So it's like this kind of a thing. This is now the anode part of rotating anode. And the point, this is the tube. This is about 30 centimeters or so. In principle, it's a very similar, and there's a very nice cartoon. So you need a rotor. You need to rotate the anode. That's why it's called rotating anode. And now it's not shooting in one particular place. It will shoot a radial area in here. And if you look carefully, maybe you can see this is the more lighter area in here. That is where the X-rays have been shot. It goes in here. And this allows much higher power because this tolerates more power. So this kind of a thing, if we do a rotation, the X-rays are, as earlier, created 90 degrees from the direction of the electrons. It's the same way. It comes here, out, but it's much more powerful. And this was used previously on a protein crystallography work. These kind of things is what we call the 9 kilowatt rotating anode systems. And the only difference is that the light, the beam is more bright, is more strong. There's nothing more different than that. So that's the reason for this. And then it was considered to be an in-house analog of a synchrotron, because synchrotron is the most powerful thing to be done. But the point in there with the rotating anode, because it's more sophisticated technique, it requires much more things. For example, it requires that this has to be in a high vacuum. And then in order to make a high vacuum inside this kind of a thing, it's not simple and easy. So you need pumps. And then the running costs for this kind of rotating anode are 5 to 10 times higher than with what we call the sealed tube, the previous one. And that is why the reasons these are not that much used. Luckily, this is now changing, and actually our instrument, I already told you, our instrument is using rotating anode, but it's only 1.2 kilowatt, and it's a microfocus, so it's much smaller. So this is also developed a lot. But the actual idea is that it needs more gear to run it. And then what is now the let's say state of the art? This came about 15 years ago, roughly, yes. It's so-called microfocus saws. And in principle, again, it's the same as the traditional tube. It is the same size, roughly the size of this. But how it's done is that now the focus where the electrons are hitting is really small. So because in the conventional NMR X-ray tube is about 1 centimeter, the anode. Here it's microns, tens of microns. So it means that it creates the X-rays to a much smaller area, and then by volume, by the power combined by the small size, you will get much more out of it. So it's more efficient. And what it leads that the point in there is that, where is it? It's not mentioned yet, that they operate about 40 watts. So we still need the high voltage because we need the speed of the electron, but now we don't need to have a huge powers for there, so we can have, it's like a light bulb. And now it looks like this. So the X-ray tube is inside here. This is optics. The X-rays comes from this side. And now, because it's so compact, easy to do, you can have 2 of them in the instrument. So that's what we have in the other instrument. We have copper and molybdenum radiation in the one instrument. And then by the computer, just you push a button, okay, change the radiation, and it changes the radiation. And that's the idea. So this is called the micro source X-ray tubes. They're inside here. And the only difference now is how you create the X-rays, mechanically or technically. And then the point on here is that we need the electronics and so on for this. But this is the current technology. And if you are going to buy a normal diffractometer now, very likely it will have this kind of a micro source available in there, either 1 or 2. These are also rather expensive. This is about ₹1,000,000, 10,000 euros. But they last also something like 4 to 5 years maybe. at the current stage. So they are a little bit more expensive than the stationary, the classical ones, but they are also 20 times more powerful. So you save energy and time when using these kind of things. And in our university and our department, we have both. We have this and the rotating anode system for that. But that is just the technological side of how you do this. And then, of course, finally, the synchrotron radiation, the question how it's done. So it's you accelerate the electrons in here, and then you get a huge speed. Look here. It's 10 to the power of 6 electron volts. So that's the idea. That's the speed that is used to do this. And the energies are there. They're high energy electrons, and then it creates a high energy X-rays. But in principle, the wavelength, once it's coming out from here, let's say from this one, then it's the same as in-house instrument. But this is the diamond light source here. So it's a facility which needs 100 to 200 persons to run it. So it's easy to understand that no single department or no single university can have this. Australia has 2. UK, I think, has 1 or 2 or so on. Sweden has 1. Germany has a few. France has a couple of 1. And there is this CNRS is a big facility for this. And the point is now that only one of these stations, they call these stations, only one of these stations could be single crystal X-ray diffraction. You can use many other techniques in here. So when we buy an instrument, it's only making the X-rays, and we can use that. We call it diffractometer. But synchrotron can do many other things also. And only one, typically one beam line is dedicated. So in this kind of a thing. So you can see here now, each of the station here is doing a different thing. And one of them could be dedicated to protein, for example, protein crystallography. But it's extremely difficult technique, very tedious, very expensive. And then you have to, what you have to do inside, in-house, if you have your own instrument, you just grow the crystals and walk to the lab and do the work. In here, you have to either transport the crystals there or go and pick them up and bring it there by yourself. And that's the idea. Sometimes you have to protect them. They are very sensitive to your air. You have to keep them in dry ice or liquid nitrogen and so blah, blah, blah. Having this in airplane will be really complicated. So the use of synchrotrons is not very useful, let's call it like this. But protein structures are exclusively done by synchrotrons. Now, and the point in there is that because we have these many transitions possible, but we want to control that with the power, what we are doing. And the idea is there that now, this is now the, you look here, this is now the radiation, and then we have the 2 spikes there, beta and alpha right there. And now what we want to do, we want to remove everything else. We need the one radiation only. And this is what we are doing. So now if you look for this picture, it's the same as in here, but it's only enhanced image. So this is the background radiation, and beta is here and alpha is here. Alpha is now combined, alpha 1 and alpha 2 is combined. So what we have to do, we now try to do a trick where we remove this one. And now you can see there's this dotted line now. This so-called absorption edge. It's another element, a metal typically, which has an absorption. So it absorbs X-ray radiations on this area. And the point is that if we find a metal, typically a metal which has this kind of a thing, by placing this metal in front of the X-rays, it will cut out this part. It becomes this. You can see what happens. So these are in the same scale. So when it's applied, you shoot X-rays through a metal, and the metal has this kind of absorption edge. It will cut down the intensity of the alpha radiation, of course, that absorbs also alpha. But what happens, it absorbs quantitatively the beta radiation. As you can see now, there is virtually no beta radiation. We can use this. This is what we aim. So then this is called monochromatic radiation. And the idea in there is that we call it in here, which we use the metal, we call it a filter. So it's an X-ray filter, and then these are used to create monochromatic radiation. So for example, if you take a zirconium metal, then it will do this. That would be like a molybdenum radiation, K alpha and K beta in molybdenum radiation. If this is zirconium, that will be the product. So in this way, we can do this. And it's easy for us to do this. This is a simple business done 100 years ago to select this thing. So if we are using, let's say, nickel, we can use cobalt as a filter. If we use copper, we use nickel. If we use molybdenum, we use zirconium. And the point in there is that now these are the anode materials, but we only use two in real life. So we use either copper or molybdenum. So then we can use either nickel or zirconium filter. But that is a very old-fashioned technique. So I've used my first of my instruments, what I was using 40 years ago, nearly 35 years ago, was having molybdenum radiation and zirconium filter in there. But it worked fine. So this was what we got out, and I was able to use it in my studies. But the point in there is a better way to do this. So we call them beta filters because they filter the beta radiation out. But the more clever way of doing this is to use a device, again a device. So you notice now that the X-ray diffraction and the instrument so is a device. They're combination of many devices because we have to do certain things in there. And the one thing what we are now doing with this is to make it monochromatic, and then the device is called monochromator. And the monochromator can be like this. It could be like curved silicon. So we create here from the anode, we shoot electrons, we create here, this is the X-rays. And now these X-rays contain both the alpha and the beta radiation. But now the point is because we have a curved detector, and it will be diffracting from this curved silicon. In a very similar way, it will diffract from our own crystal. But now, because it's curved, it will make, in a sense, that a certain direction of these radiations, alpha is diffracted, but beta is not. So the beta goes through, and only alpha remains. So this is the same trick as with the filter, but this is mechanical, more or less. So it's using diffraction from a curved silicon. And this was the system what we had in the instrument I started to work with in the middle of the 80s, so nearly 40 years ago. And the idea is that this was the second option to monochromatize this. And then we have monochromatic radiation. It goes to the sample, and now in the sample it diffracts. This is our crystal. It goes to the detector, and we then measure the diffractions with the detector. That comes later on. But this is how we can make the X-rays monochromatic. And there it's germanium, silicon, graphite crystals. And they are based on Bragg's law. So we, in a sense, exclude the unwanted wavelength by this. But then the other one is that you can also do a new technique. You can use mirrors and collimators like this. So here is the X-rays is coming from that side. Now, by moving and changing the spatial orientation of these two things here, they will also diffract now, but they can diffract so that it actually never comes out, the radiation. So we can, it's the same as the monochromator, but now it's like a single tube. And this we called either a mirror or a collimator. The idea is that it collimates the X-rays and removes, it focuses the X-rays and removes the unwanted ones. And that is the idea. And this is how it's now done typically with the new instrument. So this is called the collimators, new instruments. And then this is the idea. So it comes here from X-ray source. Now there's a capillary that will focus it all these things, and we will have a new focused beam, which is focused. It's much more brighter because it's been focused. And then the other radiations are out. There is no, it's a one thing which is coming out, is pure radiation, what we want. And that is the idea. And then this is the new modern instruments. So like what we have, both new instruments, even this 14-year-old, 13-year-old instrument is also still has the similar, already has this collimator type of thing. And now there is even additional new features of these. You can even modulate, you can split the beam. We can also do additional modulations on the radiation, on this electronics or the optics produced there. And this is the actual cartoon for these kind of things. And these are all helpful for having a coherent, pure X-ray beam. And this is actually what we need. So this is, I will not go through, this is a powder diffractometer geometry, but these are the simplified versions of now the whole diffractometer. So in here, we now create, this is a rotating anode. We create the X-rays, we put them through a monochromator or a filter. Now we do this with the monochromator, they will then hit the crystal. It's monochromatic. This instrument part here is called the goniometer, that's the robot, which rotates the crystal. And now when it shoots there, most of these crystals, most of the X-rays goes through of the crystal, but tiny, very tiny fraction will diffract. And this is now what you see in the detector. That's the diffraction image. And this is what we need. We don't need anything else from this instrument, but we actually, this is the data what we have. And now this is the different geometry of the same thing. So goniometer, detector, monochromator, and X-ray source. So now, why X-rays? I needed viewing molecules. Remember, I already discussed this with you. So the point, what we can see with the optical microscope is the wavelength. The wavelength, the light is needed for this. And this is a cartoon. So you have your eye, a light, a larger object, your eye, you can see an object. But when the objects get smaller and smaller, you cannot anymore, your eyes are not able to focus on it because it's too small. So what you can do is a trick, which is now 500 years old, is the microscope. So you use optics to make the image bigger, virtually bigger. It's not increasing in size, but its image is getting bigger. And that's the idea. But the point is that there is a limit for this, because it's the limit comes from the wavelength of the visible light. And the point is the maximum resolution with the optical microscope is about 400 nanometers. So this is about the 1/2 of the wavelength of the visible light. And 200 nanometers is actually 2,000 ohmstroms. And remember, our scale is 1 or 2 ohmstroms, what we are talking about. So light is out of the question. So we can't use microscope. It would be nice to look your molecules and atoms with the microscope, but we cannot. But the point here is an image of a fiber which is being magnified by 500 times. So you can see very tiny objects, but we cannot see anything which is bigger. But that's the maximum theoretical resolution is lambda over 2 on these things. So the point is if lambda is 1, so the wavelength is 1 ohmstrom, then the maximum resolution is 0.5. And now we can get a better magnification by using electron microscopes. And these electron microscopes, of course, can go from 0.2 to 200 nanometers. 0.2 nanometer is already on the molecular scale. So this is about 2 ohmstroms. So in here, you start seeing, with the highest possible resolution, start seeing molecules. And the point here are some images. Look, very nice looking animal. It's a tube worm living. So it's fascinating to see this tiny object. We are looking, of course, molecules, but not the living creatures. You would consider this is a horror movie, but no, it's real life. Or then you can have crystals. You can measure, of course, crystal sizes for this. And then you can, this is an AMF tip. You can see that this is actually what is used. So this is what microscopy can do. So you have SEM, stems, and so on and so on. I will not go into these details because this is out of the scope of this. But in principle, the technique is the same, but it's using electrons in many of the cases. And you might have heard about electron diffraction. Electron diffraction is in principle the same as X-ray diffraction, but it only uses electrons for this. And then what you have as STMs and TEMs, solution images, like you can start seeing what I would say a ghost or the image of an atom. You can't really see it, but you can like visualize, okay, these are atoms. very well organized in there. Or you can do a nanoparticle microscopy, and you can see layers or crystalline structures here. This is also the 2D material scientists speak about crystals. But these are 2D crystals, so they are not really 3D crystals, what we need. So we can image these things, but we can't get diffraction from them because there is on one layer of atoms. But they call these 2D crystals because it is crystalline structure, but only in 2 dimensions. And here, what you can do with the AFM, you can actually nearly see the atoms and bonds like in here. This is a very nice image, and here is the molecular model cartoon showing that, okay, this might come from the hydrogen bond on that. So you are on the edge of nearly seeing the physical image of a bond. But this is not weird. And here you can see are these pentacene structures. So that's the idea. These are the pentacenes on the surface. And these are images you can see here. Okay, now, is this a bond, hydrogen bond, or is it hydrogen or not? It's difficult to see because it's different. But for our purposes, we are looking even deeper. So this is not enough for us. So we have to have an called atomic resolution. We have to see individual atoms. But the idea is now, and you can have these field emission transmission microscopes for that. And then the resolution for the atomic microscope is on a scale of 1 or 2 nanometers, which is about 10 or 20 angstroms. So that's the idea. We can see this kind of a thing. And then we can use X-rays also to do 3D imaging, which is called tomography. And this is the idea. You can see inside an object or the structure of that. That's a material science or technique. And you can, for example, have a block of this kind, and then with this you can image. Or MRI, you can have an image of your brain. And that's impressional done with the X-ray tomography. And now, to view molecules in atomic level, so the wavelengths is being used. What we are using are 0.5 to 2 angstroms. So we have 2 radiations, 0.7 and 1.5. This is what we use. And this is the actual idea of what we are doing. So the point in here is that here we have our crystal. We need an instrument to record the diffraction. So this is the detector. Then we have to transport. We have to modulate, we have to tune the data in a form that the computer can read it. Computer is doing all the calculations. It actually tries to locate the phases from this data. And then there are you. You are the person to do the work with the computer. And then if everything goes well with you and computer, you can create the phases. And when you get the phases, the computer programs can create an electron density map. And this is actually the product. This is what we see. We don't see the molecule. We see the electron density map. So we see this kind of a thing. Look here, the big hills here. This is what we see. And we have to decide ourselves. And this is nitrogen, and this is carbon, and so on and so on. There are some hints and this kind of additional things which will help us. But that's the point. So this part here now, the diffraction image looks like this. And later on in the course we go through, we will see more of the examples of these images. And now there was a question about the reciprocal lattice point. So each of these diffraction spots represents one particular part of the crystal where the diffraction from that space happens. And it reflects itself as a point here in the detector. And we can consider this. And later on, you will see where this comes from and why it's needed. Because each individual thing is a single part of the whole information. So the information about how the atoms are organized in this crystal is here inside this diffraction pattern. But each of these individual tiny points contains a tiny fraction of the information. So what we have to do here, we are doing the same thing as with the microscope. We take all these things and we focus them. And we collect them. We collect all the information into one. And then later on, I will show you as a reference also how it can be, where it comes from. So we call this an image, a diffraction image. And then we collect the images. And then for that, we need the instrument to do the movement. Because if we just keep the crystal in one position and shoot X-rays, we get one image. But this one image is not enough for us. So we need to do this. And this is why we need the instrument themselves. And that's the idea. So there's a lot of different steps what we are doing. And what we are doing in this course, we are going a little bit on theory on here, what happens and why this happens. We look for the crystals, how they look like. We learn how to make them. Then we know if we can get this done, we get the data. What can we do with this with the computers and so on? And finally, visualize the structure, use this computer programs to visualize the structure, because what we are showing is really a model which is placed on top of the electron density. So we are having two things. We have the real electron density from our crystal and then our model. And they have to interlap. They have to be the same. And it's quite often the case that it was okay that how you describe your molecule. So we use chemistry terms to describe the molecule. Okay, what are the atoms? But actually X-rays don't know the atoms. X-rays only know the electron density. So we know how much diffraction power is on that position. And this is something which is very important for us to know. So the idea, and the X-rays are scattered from the electrons, and the structural image is based on the time average electron density. Because of course the time average means that because the measurement takes either minutes or hours or days, but that's the case. And now theoretical resolution for molybdenum radiation is 0.4 Ångström. So we can see separate objects which are separated by 0.4 Ångströms. There is no atoms which are so close. But it actually means that we can get more information. We can do electron density studies with this resolution. And it's a special technique, the electron density studies, but that's the idea. And there you can see what is the magnification when we are doing for the X-rays, 10 to the power of 8. And that was that. 1 minute past 1. And now, if I understand it correctly, we will have a 1-hour break now. And then we return and change gears. That will be then more soft thing. I'm the hard guy. And then the softer guys will speak about these things, but I will not be too hard anyway to you. So that's the idea. So we will go like this and have a break for 1 hour. Yes, okay, great, thanks.